All right, I want to talk to you about one of the types of projectile motion problems that we have, which is called the horizontally launched projectile. And in this case, we sometimes call this a cliff type problem. This is where you have a person or a thing or whatever that's starting at some height and launching an object horizontally. So it's going to have an initial VXO, an initial x velocity, but it's not going to have a vertical velocity. Also, a lot of times you'll just be given the initial starting height. So that would typically be a given value, or maybe you're given the information about how far this projectile goes, as it projects down, and then you have to work backwards to those things. In any case, with any projectile motion problem, what you want to do is set up your variables by just writing those out. So I have my initial and final x displacement, I have my initial and final x velocities, I have an x acceleration, and then I have all of those same things but for the y variables. So it seems like a lot to keep track of, and honestly it is. However, the point of this video is I want to show you that in a lot of cases we know so many of these and we know so much about the scenario without even addressing any numbers. So without giving any values here, let's see what we know. We know that the initial x displacement is going to be 0 because it hasn't gone anywhere. This before the problem began, it hasn't gone anywhere. We started 0, and therefore we know that the final x is going to be some positive number, in this case the way I drew it anyway, and that's going to be the range. So when you hear about the range of a projectile, that's how far horizontally it's been projected. For my VXO, it's some value. Typically it's given, not always though. And to address the final x velocity, we have to consider the x acceleration, which, remember, in many of these cases, or pretty much all of them, we ignore air resistance, and so we have 0 x acceleration, and therefore we know that Vx is equal to Vxo. So once I know that value, I'll know that what this value is as well. As for the y's, we already said that the initial y is your height, and therefore your final y is going to be the ground, 0. Now it is possible to call this 0, the initial y, and then call the final position some negative value that's equal to the height. It doesn't really matter. It works out the same because it's the change in displacement that actually matters. So pick what works for you. I like this way. Makes the most sense. Since you are actually starting at that height, we typically consider the ground to be our 0. For our y velocity, this is important. We know that it's 0. And we know that because we said this was a horizontally projected projectile. If it was launched upwards or downwards with an initial y component to its velocity, that's still doable, but it's going to change the math a little bit and make it a little bit trickier. So in this case, this is a horizontally projected projectile. I know that we will have some final y velocity because it will be traveling downwards by the time it gets towards the ground. So I know that that's going to be some negative value, so I can at least put that in there. And that's because gravity is negative 9.8 meters per second squared. So all of these things we know right away when we look at a horizontally projected projectile, just by virtue of the circumstances and the situation. So when we do this, with any actual word problem or scenario, you would likely be given values either involving the initial scenario of how high off the ground and how fast it's projected, or maybe that you need it to land at a certain range or things like that. And then you can take these values that you can go to your kinematics equations and you can start solving for the missing variables. And that is a horizontally projected projectile. Hope that's helpful.